Today we're going to review what the two different waves look like and how they act. The first wave we're going to look at is transverse waves. So what does a transverse wave look like? It looks like what we traditionally think of waves, which is the up and down motion. So I'm going to show you that. So up and down and up and down. That's our traditional wave. That might not be perfectly drawn here, but that's kind of what we normally think. So in the next picture, you're going to see it. Here's what it would look like beautifully. So draw this on your paper. And you can see it goes up and down above the line, the resting line, the resting position. And now we need to talk about the parts of the wave. So as far up as it goes above this horizontal line, the resting position, is called the crest. And the furthest it goes down is the trough. So think pig trough, what they eat out of. Okay? And then, of course, to measure the distance it's gone, we measure either from crest to crest or trough to trough, and we call that, from between each one, wavelengths. So you can see here, you've got your crest up at the height, the trough at the bottom, and your wavelength. So I'm going to make that a little bit nicer looking. And the other thing I didn't mention is if you try to measure from the resting position up to the top, you have the amplitude. So don't forget that. That's a measurement of how tall the wave is. And if you notice, the amplitude actually is the same length down to the trough as well, but we usually just measure it to the crest. So make sure you have this on your paper, the parts of the transverse wave. We want to measure its wavelength, how long it is, how far it goes, but we also want to measure how tall it is by using the crest to the resting point, and then how low it goes down to the trough. All right, what does a compression wave look like? So this one's a little different. This is the slinky effect. So this kind of looks like you might have some really close, you might have some really far apart. That's what I call the slinky, and of course I want to make that nicer looking. And as you see here, there are some links that are closer together, and those are compressed. And then you have some, you can see here, that are further apart. And those are called rarefactions. And if you want to see how long this wave is, you would measure between usually you measure between compression and compression. So between where you see a compression over to the other compression, right down here, you would have your wavelength. So let's see that in a picture. So between compression, and then your rarefactions, think that there's less, that's rare to have the links, whereas compression, you're pressing them together more. And you have your compression wave. These are what we usually consider kind of like our sound wave. They're pressing through something. Now we need to think about how does a transverse wave and the medium it's using move. So the transverse wave itself, if you remember when we shook the rope, the wave will travel down the rope. So it travels, which way would it travel? It would actually travel the rope down the rope, so it would travel what's called parallel to the resting position. But then if you notice, the rope went up and down, up and down, up and down. So the medium actually goes up and down, whereas the wave itself, as it travels down, it actually goes. So they're going perpendicular directions. So they call it propagation, is the way the wave moves. So this is the actual wave moving down here. But then the movement of the particles, which is the medium, is going up and down. So they're going perpendicular to each other. The medium itself, the rope, went up and down, but the wave itself traveled down parallel to the resting position. Well, now, if we did the compression wave, which we did with the slinkies, now you have a little different here. So remember, everything kind of squeezed together and pulled apart, squeezed together and pulled apart. So the wave would go travel down with the slinky positions, and then it would kind of bounce back and come back. Well, the wave does that. Remember, it went down. But then, if you notice, the slinky physically did the same thing. So the medium actually does the same thing. And these two lines are parallel. So they move, the compression wave and the medium move parallel to each other versus the perpendicular way that the transverse wave moves. So here's a better picture of that. The wave moves in this direction, but we also need to mention that the medium does as well. So don't forget that. It's not just the wave, the medium, they both go in parallel. And that's it. If you need additional help, please come see me.